Okay. Hi, everybody. I am going to do some problems from Chapter 7. And, I'm trying to pretend that we are in class. And anyway, I hope this works, right? So largely Chapter 7, we have been talking about looking at some sort of trade-off between risk and return, right? And we're constructing a frontier of potential portfolios, right? And we have used that, the formulas in the textbook. This is hard to do because I haven't taught this yet, but I'm making the recording for it. Anyway, we have, this would be the minimum variance. Right? And so we have a minimum variance portfolio where the standard deviation or the variance of this portfolio is as small as it can be. And then we decided that there would be a portfolio where it was optimal, right? In other words, it would be on the efficient frontier of portfolios, but it's better than the minimum variance. And that's a line tangent to the capital allocation line. Okay, so that's the idea of what we're doing here. This is largely what happens in Chapter 7. I want to give you two formulas. Two formulas that to calculate these things. So we'll do this. We'll say the minimum variance portfolio. I'm going to swap to a better marker. So we have the weight and debt. This is to construct that portfolio. It's at the minimum of variance, right? The weight of debt would be variance of equity minus so this solves numerically, and this is actually a calculus problem that if you were to optimize the weight, this would give you the weights. Obviously, if you swapped equity and debt, and here equity, swap it around, you could do it the other way. And on an exam, you might want to do that just to test yourself. This is the equation. If correlation were -1, would be the weighted debt is sigma equity over sigma debt plus sigma equity, which is in your textbook. Okay, so that's the formula for the minimum variance. Now we also want to solve the optimal amounts in the optimal portfolio. Yeah, the weights. So this is the the optimal Sharpe ratio portfolio, right? That's the one up here on the frontier. So again, you can interchange debt for equity, but the weight of debt the expected return on debt over and above risk-free variance of equity okay, minus the risk premium on equity, the expected return on equity over and above risk-free, times covariance of A between equity and debt. That's a numerator. And the denominator, the risk premium on the debt times the variance of the equity plus the risk premium on the equity times the variance of the debt minus the risk premium on the debt plus the risk premium on the equity times the covariance between debt and equity. Okay, and then so this gives you your weights in debt, and then you must solve this equation. The optimal amount of Y, right, is the amount of money that you put into this risky portfolio based on someone's level of risk aversion. Which is level of risk aversion is A, remember? Sigma squared of the portfolio. Okay, so we want to, this is just a review. And now I want to do the problems associated with this chapter, okay? Okay, okay, I went and got a better marker. Now, we're going to do chapters 7 problems. This is information we have. I'll put it over here. Can you see if I write over? Yes, you can. 3. We have 3 mutual funds, a stock fund, a bond fund, and a T-bill fund. T-bills return 8%. Stock returns 20%. Standard deviation, T-bills, risk-free, right? Don't need nothing. We don't need anything. Standard deviation of the stock account, of the stock mutual fund is 30%. Bonds return 12%. 15% mutual fund. Correlation, row, 0.10. Okay? So this is information we need to solve 4, 5, 6, and 7, and then maybe 8. 4. The investment proportions in the minimum variance portfolio. I just did a review of that, right? We need covariance, right? Covariance between stocks and bonds is equal to rho, which is equal to 0.10. So 0.10 times 30 times 15, 45. We said correlation was 10. So we have a covariance then of 45. Let's use the formula. Weight in debt, sigma equity squared, variance of equity, right? Minus the covariance between the two, right? Variance of the stocks, variance of the bonds, okay? That's a formula we use. Weight in debt, 30 squared minus 45. Thirty squared, 15 squared, right? Sigma stock is 30, so squared minus 15. Sigma bonds minus 2 times 45. This is equal to okay, so we found the optimal amount of money to put into the debt fund to create the minimum variance portfolio. Just for kicks, we'll do equity. You don't have to do this if you're confident in that, but what's different here? This is equity, we're going to use debt. Covariance, debt and equity, and This is the same, isn't it? 900 minus 90, which becomes over, right? Essentially, this is the part that's on, this is the only part that's different. So this becomes $17.39. Naturally, they must sum to 1, right? So, so we have the optimal weights, right? I'll put this over here and then erase. So the weight in debt, 0.8261. Weight in equity, 1 minus that, or 0.1739. Now I'm going to get rid of this because we have to solve the rest of the equation, or the rest of the question. The expected value and the standard deviation of the rate of return. Expected return of your portfolio is simply the weight of each times the return on each. So 13.39% return on this portfolio with these weights. Yes? Variance is a different thing, remember? So we had the formula for variance. Squared times 15 squared plus squared covariance, weight and equity, weight and debt, 2. Okay, this is this. So we have sigma squared portfolio becomes 1 193.689, right? Square root of this, sigma of the portfolio, is simply the square root of that, 13.917. Okay, so there's 13.917% standard deviation in your optimal portfolio and a 13.39% return. Okay? All right, let's have a look at, that was number 4. So number 5, calculate the investment opportunity set for the 2 risky funds in increments of 20%. So we're using these numbers, but instead of calculating these weights, we're going to use increments of 20%. This is, I believe, number 5. Yes, this is number 5. We've got the same data here, but we're going to do it in increments of 20%. All right, let's see what we get. We have weight in equity, weight in debt. So clearly this would be 0 and 100. Whoops. $20 and $80, $40, so all we're doing is changing the money that you're putting into these accounts, okay? So the expected return, this would be 0 times 20 plus 100 times 12. 12% return. 100% of your money is in the bond fund, right? Earning 12%. Here, 20% of your money times a 20% return in the equity fund, plus 80% times 12. This is a 13.6% return. 40 times 20 plus 60 times 12, 15.2. 60, 20 plus 40 times 12, 16.8. 80, 20 plus 20, 12, 18.4%. 100, 20, 0, 12. It's got to be 20. Okay? I mean, that's very straightforward, right? So the next part is not so straightforward. What is the standard deviation? I'm going to write the formula again, so I want to make more room. Yeah, so this just becomes a matter of plugging in the numbers. For here, 0 squared, 20 squared, 100 squared, squared, 2, 100, 0, 45, 15. Look, you've got all your money in debt. You've got all your money in the debt. The debt standard deviation is 15%. It's 15%. We'll do another one. 20 squared, 20 squared, 80 squared, 15 squared, 2, 80, 20, 45, 13.94. The standard deviation associated with 20% in equity and 80% in debt. Okay? And these just go, et cetera, right? It would be a waste of your time and mine because you can do this at home now that you know how to do it. I have 15.7 here. I have 19.53 here, 24.48. What do you think this one's going to be? Yeah, exactly. 30, standard deviation, 100% in equities. Okay? So that's question number 5. We did 4 and 5. 6, I say the question asks for a tangent from the risk-free to the opportunity set. What does your graph show for the expected return and standard deviation of the optimal? Well, we just did that, didn't we? I know, we didn't draw a picture. Let's erase this. Everybody good? So the nice thing about having a lecture on video is you guys can stop, go get a drink, have a piece of cake, whatever you need to do, right? Not like in class where if you brought cake to class, you would have to share it with everybody. So I just got booted out of 101, and so I'm down in 109 now. And anyway, number 6 says just, I think it says, draw a tangent from the risk-free to the opportunity set. What does your graph show for the expected return? So look, the previous one, we had in increments of 20%, right? Sigma and expected return. There should be some sort of efficient frontier that we're creating, risk-free. So given the amounts that we used, they're asking what's this and what's this, right? Sigma and the return. This is of your portfolio. So that's all. You know, you just have to draw a rough picture like I did here. Let's have a look at number 7. Solve numerically for the proportions of each asset and the expected return and standard deviation in the optimal risky. At the beginning of this recording, I put the formula for the optimal risky on the board. But we'll do it again. We solve for this question. Solve numerically for each for the amount of each asset in the optimal portfolio. This is the portfolio, of course, that's tangent to the capital allocation line from the risk-free rate. Notice on this one, I did it a little differently. Instead of saying covariance, I'm using sigma debt, sigma equity, and correlation, right? They're interchangeable. And again, correlation, sigma debt, sigma equity. Okay, so that's our formula to figure out the amount of each asset in the optimal portfolio. Let's plug in our numbers. You have all the information over here. Of course, we know that sigma debt, sigma equity times correlation is 45. the covariance is 45, right? Okay. All the numbers from our formula. We do the math associated with this. Five, 4, 8, 4, weight in debt optimal. Weight in equity is simply 1 minus the weight in debt. 1 minus 0.5484 weight equity. So let's see, what's this equal to? 0.4516. This is optimal weight equity. Okay? Now, so we know this is what you're doing. Before, the question 4, I think, wanted to know what's the weights in the minimum variance. This question is asking us what is the weights in the optimal portfolio. So I'm going to put the weights over here so we have them to solve the rest of the problem. Okay? Everybody's good. Let's erase this. Because the rest of the question says, well, what's the return and standard deviation in that portfolio? And this is easy, right? Excuse me. This is, so the return, the expected return in your combined portfolio with optimal weights is 15.61%. Sigma squared portfolio. What's the variance of the portfolio? Again, weight equity squared sigma squared equity. Weight squared sigma 2 weight debt weight equity covariance returns on debt return on equity. Yeah, we all know that by heart anyway, right? This is equal to Sigma squared portfolio, 273.5. Sigma portfolio variance, standard deviation, 16.538%. Okay, so that's number 7, I think. Number 7 in the Chapter 7 problems. And then what? Number 8 says, what is the Sharpe ratio of the best feasible portfolio? Well, we all know, right? Sharpe. Is some sort of a measure of reward over risk. Expected return, risk-free, sigma p. Yeah, that's all, right? So the expected return on our portfolio, 15.61% or 0.1561 minus our risk-free rate, T-bills, over the variance of the portfolio, 16.538%, or 538. The Sharpe ratio of the optimal portfolio is 4602. Okay? So that's 4, 5, 6, 7, and 8 from Chapter 7. And you guys can watch this instead of class. And my feeling is that this might be more helpful because you can pause it and say, what? Right? But it is very important. And I imagine that you might see this again. Okay? All right, everybody, I hope you all have a very nice Easter and a little bit of a break. And we'll see you Tuesday.